So, in the last tutorial, I stated some results in dimension theory. So, today we will see some applications of those results. Okay, let me first recall the definition of dimension of a topological space. Let X be a topological space. Then the dimension of X is defined as the supremum of all the natural numbers n such that say z0 is inside properly contained in z1, properly contained in up to, means this is chain of some closed subsets of irreducible closed subset of X. So, suppose this where each zi each zi is closed and irreducible. So, dimension of this topological space is the supremum of all those natural numbers such that it has like length n chain of irreducible closed subsets of X. Okay. And dimension of a variety will be the dimension of means its underlying topological space. Okay. So, now I will prove a proposition. Let Y be an affine algebraic set. Then dimension of Y is equals to dimension of AY, where AY is the coordinate ring of this affine algebraic set. This is nothing but the coordinate ring. Of Y. Okay. Now proof. Let this Y is affine algebraic set. So, we take this Y is in AN, say affine n space, this is closed. Then all the closed irreducible subsets, means suppose this Z say is a closed irreducible subset say of Y. Then we know that this ideal of Z, ideal of I is inside ideal of Z, ideal of Y is inside ideal of Z, and this this ideal of Z, this will be a prime ideal. Prime ideal, yes. This will be prime ideal. So, we see that there is a 1:1 correspondence between the irreducible subsets, irreducible closed subsets of Y and the prime ideals containing IY. I of Y means I of Y is the ideal of the algebraic set. So, there is a 1:1 correspondence. prime ideal containing I of y, I of z is the prime ideal containing. So, there is a 1-1 correspondence between the 1-1 order reversing correspondence, correspondence between the irreducible subsets, irreducible closed subsets of y and the prime ideals prime ideals of ay containing sorry, not ay, the prime ideal of k say x1 up to xn, because we have taken y is inside an. So, prime ideal of this containing I of y. So, now we know that from this observation it follows that dimension of y will be same as dimension of ay, right, because the dimension of a ring is the Krull dimension. Krull dimension means this means that it is a chain of prime ideals, and here dimension of a topological space is chain of means length of the chain of the maximum length of the chain of irreducible closed subsets. So, from the definition it follows. Okay. So, this is one proposition. Now, the next one, proposition, we take this proposition 1, say proposition 1, here this is proposition 2, say let y be a variety inside an, be a variety, it means that this y is a means irreducible closed subset of an. Okay. Then y has dimension n minus 1 if and only if this y can be written as some v of f, 0 set of some polynomial f, where f is inside this k x1 up to xn, say in variables, a polynomial which is irreducible, means there is a irreducible polynomial f inside this invariable polynomial ring. So, y can be written as means y has dimension n minus 1 if and only if y can be written as 0 set of a single irreducible polynomial in n variables. Okay. Now, proof. Here one thing is sure, right, that f is means one side is easy, means this side is easy, that when f is irreducible polynomial, is an irreducible polynomial in k x1 up to xn, then yeah, uh, then the ideal, we know that you know, yes, from this previous result we know that dimension of y will be equals to dimension of ay, right. Now dimension of ay is nothing but dimension of k x1 up to xn modulo iy, right. Now in the last tutorial I stated a result on dimension theory. From there we can see that this is nothing but dimension of this k x1 up to xn minus this yes, height of this iy, right. So now from there we see that, so this is equals to n minus, now the height of iy, because what is iy? Iy is equals to I of v of f. Now because f is irreducible polynomial, so the ideal generated by this f is will be prime ideal. So this will be equals to this ideal generated by f. Okay. Now height of iy, so this is now f is a which is irreducible, sorry, non-zero. Wait, I have to means where if is a non-constant irreducible polynomial. Now the height on this height of iy, this will be equals to 1. This follows from Krull's principal ideal theorem that this iy is generated by iy is the minimal prime ideal containing f, and f is neither a zero divisor nor a unit. So we can use this Krull's principal ideal theorem. So from there we can see that this is equals to this height of iy is equals to 1, right. So using Krull's principal ideal theorem, principal ideal theorem. Okay. Now the other part, suppose dimension of this y is equals to n minus 1. Okay. Now from there we can see that so this dimension correspond dimension so from here we can see that dimension of sorry, yes. So again we will use the same thing. From here we can see that height of iy, this will be equals to dimension of the same thing k x1 up to xn minus dimension of ay. Now dimension of ay is equals to dimension of y, and here dimension of this is n, so it will be dimension of y. So this is equals to 1. So height of this this prime ideal Iy, this is equals to 1. Okay. Now we know that uh, we know that that yeah, this kx1 up to xn, this is a UFD, right? Now again in the last tutorial I stated that Noetherian domain is UFD if and only if its height 1 prime ideals are principal. So this Iy will be principal. Yes, principal. So it implies that Iy is generated by a single irreducible polynomial. Is generated by a single irreducible polynomial. Where f is an irreducible polynomial okay. So done. Okay, now I will do a problem from Hartshorne. A problem from Hartshorne. Suppose Y is a uh, algebraic set, yeah, closed, just algebraic set, where Y is defined as the this 0 set of these polynomials, this x square minus yz, sorry, this is inside not an, but this is inside a3 comma xz minus x. So suppose this Y is this algebraic set in A3. So we have to find the irreducible components, irreducible components of Y, and also find the generators, or find their corresponding prime ideals, find their corresponding prime ideals. So how to do means solve deal with this problem? So solution, first observe that this v of y equals to this v of x square minus yz comma xz minus x. So we can write this as intersection v of xz minus x, right? Now this xz minus x, we can factorize it, means so x times z minus 1 we can write. So this thing we can write as intersection v of x union v of z minus 1. Okay. So this is what we have. Now we will use this distributivity property. So this will be yz intersection vx, this union vx square minus yz intersection vz minus 1. So we have this. Now we can write this as x square yz comma x, and we can write this as just v x square minus yz comma z minus 1. Now you observe that this set is equal to x comma yz. means this 0 set of these two polynomials x square minus yz comma and x, this set is equal to this 0 set of these polynomials, this x and yz. It's just means you have to just see, it's like it's very easy to see these things. So now we can write this vx comma yz, we can write this thing as vx intersection vyz. Okay. So now this thing yes, union v x square minus yz, also this thing we can write as v x square minus minus y comma z minus 1. This thing you have to verify that these two are equal. This is easy to see. Now we have this. Now also here also we can write this vy union vz, we can write union this right. Now this is equals to vx intersection vy and union vx intersection vz, now union v x square minus y z minus 1. We can write like this. Now from this previous expression we can rewrite this thing as v of x comma z union v of v of x comma y, v of x comma y and then v of x comma z, then union v of x square minus y comma z minus 1. Now these are the irreducible components of y. Why? Because this this ideal generated by x and y, this is a prime ideal because kxyz modulo this is isomorphic to kz, so this is an integral domain, so this is a prime ideal. So this vxy, this is a irreducible this is irreducible closed set. Now this similarly this quotiented by this yz, this will be isomorphic to ky, so this is also an integral domain. So this will imply that xy is prime, so this will imply that vxy is irreducible. So similarly this will say that yeah, vxz is irreducible. And the third one, that kxyz, this quotiented by this ideal generated by x square minus y comma z minus 1, this thing we can means you have to verify this, that this is isomorphic to this whole ring, then this is quotiented by z minus 1 and this is isomorphic to kxy quotiented by this ideal generated by x square minus y. Now x square minus y is irreducible in this ring, polynomial ring kxy, so this is a integral domain. So this will imply that v of x square minus y comma z minus 1, this is also irreducible. So from here we can say that these, and also observe that no one contains another. Okay, this vxy, vxz and v x square minus y comma z minus 1, no one contains the other. Okay, so these are the irreducible components. So the irreducible components are this components of y are this vx y, vx z and v x square minus y comma z minus 1, and the corresponding prime ideals, this corresponding prime ideals are this is the ideal xy, this is the ideal x comma z, this is the ideal x square minus y z minus 1. So these are the prime ideals. So okay, so I will do another problem in the next tutorial. Okay.